So this is a really complicated model. It's a model of the interdependencies among lifeline agencies and departments in metropolitan Los Angeles. And it's 139 nodes and 343 connections. There are probably hundreds of thousands of long causal pathways made up of all the nodes and following these arrows, snaking through the system. So it can be hard to make sense of, and I do recommend, of course, that you start with the visualization functions, that you let your eyes and your brain take a first pass, because our brains are really well suited at detecting patterns in visual data. But I also think that our brains can only go so far in understanding complex systems in general. So what I would like to show you right now is this is the simplest analytical feature in the Elephant Builder, which is this trace function, this trace button. And what happens when you click on trace is that you have the opportunity to view these causal paths, these long causal paths that are made up of many nodes and many arrows. So what I get when I click on one node, in this case I clicked diesel supply, is in the left panel, I get a list of all the nodes that have any kind of impact on diesel supply. These are all causally upstream of diesel supply. And I can zoom in to make these words bigger. And in the right-hand panel are all the nodes that are causally downstream, all the nodes that are somehow influenced by diesel supply, by whatever numerous complicated causal paths that exist in that model. And so if I want to look at how diesel supply affects health services provision, and I click on health services provision in the right-hand panel, and I see that I have 1,203 paths from diesel supply to health services provision, ranging from short ones, diesel supply, to backup generator function, to health services provision, to much longer ones. These are all presented in green, which means that the overall effect of each of these long paths is the same as a single causal connection that represents a same direction change. So if I have more diesel supply, then I have better health services provision. If I have less diesel supply, then I have worse health services provision. If I were to look at, say, I don't know, I'm going to guess that diesel supply and crime are oppositely related, then the paths would be presented in red or pink. That if I have more diesel supply, then I have less crime, then that represents an opposite direction connection. So I can read through these, but there's this other nifty feature that's at the bottom of the window, which is this: removal of all these nodes destroys all paths. And then it lists 4 nodes: highway system reliability, workforce availability, backup generator function, and health facility function. So if I get rid of these 4 nodes, if I just take them out of the system model, then all causal paths connecting diesel supply and health services provision, they all disappear. There's no connection then. If these nodes don't exist, then there's no connection between diesel supply and health services provision. This is a pretty nifty function, I think, because it gives us a way of thinking about resilience and robustness. If I've created this model in such a way that these causal paths represent flows of a material, energy, information, or some sort of service, if these paths represent flows of materials or services, then this cut set, this set of nodes where if I remove them, it destroys all paths, this cut set represents a set of potential points of critical, catastrophic system failure, or at least failure of that flow. If I have a larger cut set, it suggests that I have a bit more robustness. It's harder to destroy the flow from my provision node to my target node. If my cut set is really small, it means that it's easy. I just take out one node. It's easy to destroy the flow of that material or service. So this cut set is a nice way of thinking about robustness, and it can suggest opportunities to introduce redundancy into the system to improve the robustness.